Okay, this is webinar number 9 about elasticity. And I must say from the very beginning that this is a pre-recorded webinar. It's not live streamed. And it is being recorded rather in the middle of the night. So I'm not feeling totally awake, but it's a difficult agenda this week, and this is the only way to have this webinar done. But it's not because it's not live that I wouldn't have seen your reports, so I did read all of them, and this webinar is based on these reports as usual. A few short housekeeping messages. You may run into disk issues with Quantum Mobile if you are doing calculations for the project, and therefore it may be relevant to know how to add an additional virtual hard disk to your Quantum Mobile installation. And this you can do by not switching on Quantum Mobile, so just in VirtualBox, select it, go to Settings, and there under Storage you have the possibility with the plus sign to add additional disk volumes. So you can play with that if you would need it. That was all for the housekeeping. Let's jump into the science. And we started this module with a definition of elastic constants, and for some of you a repetition of well-known physics. Some people complained about that. So, well, as usual, this is because we want to have everybody on the same footing, and simple elasticity in one dimension might be familiar to many of you, but not to all of you. And even if you are familiar with elasticity in one dimension, it's still useful to connect that one-to-one to what happens in crystals. So we discussed strain and the relation between strain and, at one hand, stress, and on the other hand, elastic energy. And that relation was given by one elastic constant in one dimension and by many elastic constants if it is about crystals. This was the slide that made the connection between strain and stress for, at the left hand side, the spring, and at the right hand side, a one-dimensional material, and a similar relation for strain and elastic energy, for a spring, for a one-dimensional material, and this is then to be generalized to 3 dimensions and to crystals in the following way. The strain, which was just one number in one dimension, becomes a matrix that is symmetric, and that matrix can be written as an 3 by 3 matrix, but also as a 6 by 1 column matrix. That is called the Voigt notation. And this has the notation difficulty that in the Voigt notation you always note the double of the strain of diagonal elements. And this has a reason, we will come to that. The stress, which was just one number in one dimension, becomes a matrix 2, a symmetric matrix with 6 degrees of freedom, or a column matrix in Voigt notation, but here, for the stress, this factor 2 is not there. With these generalizations to 3 dimensions, we can write the relations that we established in one dimension in the following way. The connection between strain at one hand and stress at the other hand is given by this 6 by 6 matrix of elastic constants, These characterize the crystal, and for the energy you have to do the same multiplication, but now also multiply here by the transposed of the strain matrix. And then you get the elastic energy density at the left-hand side. Well, I mentioned we have these factors too in the Voigt notation, and I want here to illustrate that this is a necessity, that this is not just a notational agreement, or that this is not there for historical reasons. No, this factor 2 needs to be there. And I will illustrate that starting from this page in continuummechanics.org, which is a very useful site for elastic properties in general. That the link for this was available in this module, and it discusses this difference between the engineering strain and the regular strain. The regular strain, the epsilon, is what you will find in the matrix notation, in the 3 by 3 matrix notation, and when multiplied by 2 you have the engineering strain that is available in the Voigt notation. That engineering strain has a macroscopic meaning, and you can see this here. If you take this red square and you shear it in the way that is indicated such that it becomes the blue square, then the ratio between this distance d and this distance t, so that's d over t, that is the engineering strain. In this example here, if the engineering strain is 0.10, then the epsilon is half that large, and therefore the epsilon matrix will have these two off-diagonal elements of half 0.10. So that is what happens in the notation. But how can we convince ourselves that this is necessary, that this is not just some convention? And well, let's see how crystals in quantum espresso, how these relate with strain. I take here a very simple crystal, a cubic crystal. Well, it will be FCC aluminum, but for this part of the explanation, it just matters that it is cubic. So we have the cell parameters matrix, that is the unit matrix. And if I look on top of that crystal along the c-axis, then I just see this square. We have the lattice parameter here. And if I would do a quantum espresso calculation, just an SEF type of calculation, and I look in the output file, then I will see this information mirrored. Here we have the A lattice vector with 3 components, and it's only the x component that is non-zero, the B and the C lattice vector. I can in general get the length of these lattice vectors, so the square root of the sum of the squares of these 3 components, and I can get the angle alpha between the B and C direction and beta between the A and C direction, and so on. And well, this is all very trivial for this unit matrix. If you apply that, you get 3 times the same lattice parameter and 3 angles that are 90 degrees. Nothing surprising. Now I add shear strain. I will shear the crystal in the same way as that square that was shown there in a few slides ago. And that is done by adding these 2 off-diagonal elements to the cell parameters matrix. How can we see what happens? Well, I will draw literally what is written here. So this first line, that are the three components of the A lattice vector. And so I go 1 to the right and 0.05 in the y direction and nothing in the c direction. So this is my lattice vector A. The lattice vector B, that's 0.05 to the right and 1 along the y direction. So this is B. Together, this A and B span the base plane of this crystal. So I can find that by displacing A like this, displacing B like this, and here we have now the base of that crystal, of that unit cell. I can also inspect this from the output file, where I basically have the same information. And if I now apply these equations that were trivial for the cubic cell, then I find now an A and an B that are equal to each other and that are different from the unit here, and a C that is different from A and B, and that was identical to the unit. And these angles alpha beta are 90 degrees, and gamma, the angle between A and B, is somewhat less than 90 degrees. So I've clearly squeezed my crystal. Now, can we relate this, which has been defined by this 0.05, which you will recognize as the epsilon, can we relate that to this engineering strain? And well, first we go to the Bilbao server, and I put there the lattice parameters and angles of the unstrained crystal, and then the ones of the strained crystal. And that shows you the strain tensor. And yeah, I said it already a minute ago, this 0.05, these are the xy elements of the strain tensor in its matrix notation. So that's the same value that returns there. The only difference with the cell parameters matrix is this 1 on the diagonal, which are basically zeros in the strain tensor. If I now look here to these standard root tensors, these are the tensors similar to the cell parameter matrix that describe the unit cell. And now in the way how the Bilbao server writes this, here the A, B, and C are columns, and you see nicely the three perpendicular vectors in the undeformed cell. But in the deformed cell, they look a bit different. We have now a B vector with just a y component, a C vector with just a z component, and an A vector with an x and y component. And this is different from A and B in the notation in quantum espresso. So what has been going on here? This should be the same cell, but we have different components of the vectors. And well, if I formulate it in that way, you may already guess that we have to do with a coordinate system transformation here. So look at the picture. This was the picture that we had with the A and B from the quantum espresso notation. And now I rotate the axis system, and if I now look at the vectors A and B in that new rotated axis system, then I see my B vector has just a y component, and the A vector has an x and a y component, where that y component is a bit larger than in the original axis system. I can draw here the underlying square with the length of the b vector. And if I now go back to that picture from continuum mechanics, well, now you probably see the similarity. This distance d, that is more or less the y component of the vector a, our 0.4. I write it here as 0.4, while the t, that is more or less the length of this vector a, or the x component of the vector a, so the 4.02. If I make the ratio, it's 0.1, and that was twice the 0.05. So it's fully consistent. We need that notation with the double epsilon xy in order to get that engineering strain. The engineering strain is clearly the same as the intuitive definition. So it's something you could measure on a macroscopic piece of crystal by this d and t, so by these two components of the A vector. But in order to express it as a strain tensor matrix, it's this epsilon that you need here. So I hope that this helps to understand that this is not just a convention, that the mathematics really force us to use either gamma or twice epsilon, depending on what is the property you look at. And that was the point that was made on this page. Now, with this, we make a small exercise, and I give you an HCP scandium crystal, where you can find the lattice parameters on, for instance, materials projects. And I ask to do a volume conserving increase of the C over A ratio by 2%. Explain what would be the strain tensor that corresponds to that deformation. And I've put here one of your answers, where you start with A, B, and C that have these values. The angles alpha, beta, gamma are like this. It's only gamma that is different from 90 degrees. You calculate the volume of that hexagonal unit cell, either with this expression or with the very general expression for a crystal. So this combination of cross and dot products you can do for any vector A, B, C. If you do that and then you write this in terms of the C over A ratio, and you require that the C over A ratio is increased but that the two volumes are identical, then you can solve from these equations what the new A and B and the new C should be. And these turn out to be 3.27 angstrom and 5.40 angstrom. So a bit smaller here, a bit larger in the C direction. If you put that into the Bilbao server, so here are these numbers, then you get this strain tensor. 0.006, 0.006, and 0.013, minus, minus, and plus. Many people have found that, and here I repeat the procedure that you would have needed to follow for this. But there were also a few cases where you find a strain tensor that was clearly different. And in all cases, if I inspect it, there is a small mistake in the lattice parameter calculation. Like here in this example, the volume was set to be A squared times C. that would be correct for a tetragonal cell, but not for a hexagonal, where you need this gamma alpha additionally. So therefore here the volume calculation was wrong, and therefore the lattice parameters came out wrong. And in this example, what was the problem here? Somehow, and the details of the calculation are not given, but somehow you end up here with an A and B in the deformed crystal that are different. And that's why you then also get off-diagonal components in the strain tensor. So by that particular deformation, where the C over A ratio is changed and the volume is kept constant and nothing else is done to break the symmetry of the crystal, well, you should end up with a hexagonal crystal, so A equals to B, and that was not the case here. On the statement that you can use the Bilbao server to determine the strain tensor for a given deformation of a unit cell, that was exactly what we did here. Well, there most people feel rather confident. Now we move on to calculate elastic constants, to predict them, because so far we just used macroscopic properties of crystals. There was no DFT involved yet, apart from getting some information about the lattice vectors of the deformed unit cell, but that was part of the output file of Quantum Espresso that is written without the need for DFT. So let's use DFT to calculate these elastic constants. And this can be done in two different ways. We have the total energy method, where you feel rather confident about, and there is the stress tensor method, where there is a bit more hesitation for this method. And that is not surprising. I see some comments as that stress tensor method is mathematically elegant, but it takes a lot of computation time. And yes, if you want to do this properly, then it's not an exercise you can quickly do. So that is probably the reason why you feel less confident about that. Now, it was optional to work with the stress tensor method. I asked you explicitly to use the total energy method to calculate a few elastic constants of FCC aluminum. And we have here the recipes that we needed to follow for this. So the general expression for the elastic energy density, which we can calculate by DFT because we calculate the total energy. We have the volume. If you make this ratio before deformation and after deformation, well, the difference is the elastic energy, the difference between the new energy and the old energy. That's the elastic energy. So you can write the elastic energy density, and that one depends for a crystal with the symmetry of FCC, where you have only the C11, C12, and C44 elastic constants. Well, that long matrix expression for the energy density reduces to this expression. And if we now on top of that play with the deformations, and we do deformations where only, say, the epsilon xx is different from 0, then a lot disappears here, and we get this expression, which means if we calculate this energy and plot this as a function of epsilon xx, then you will see a parabola, a parabola with a coefficient from which we can determine the C11. And that is what you did. So here are your data from the spreadsheet together with data from other people. And well, that the parabolic fit here is not perfect, but we fit over a very large epsilon range. So ideally you should do the fit only over this range here of say up to 0.03, perhaps 0.05. So small deformations, and that will be a nice parabola. Here is a calculation where I repeated this with sufficiently high precision, and you see what happens if you take all epsilon in the fit up to 0.1, or you restrict the fit to the epsilon 0.03, then you don't get the same parabola, but it's the parabola with values for the small deformation. That is the one that is the correct one. That would lead to a C11 of 107 GPa. If you would take all epsilons, you would find a lower value, but it's the 107 that is the correct one. And we can compare that with the stiffness tensor that is available in materials projects. There the C11 is here at the diagonal, and that is not far away from the 107 that we found. The epsilon xy, that 2 is here because in the video that number was forgotten, but that is the correct expression. If we do this with epsilon xy deformations, that was also tried by several of you, then we get this value of this curve, again with a nice parabola. And you see here one data point at a negative strain, and somebody asked a question about that. Since somebody wondered, we were asked to do only positive strains, but why? Because I see on this picture that if you do a negative strain, your parabola continues. And yes, it is perfectly possible to do negative strains, just as with an equation of states where you could do negative pressures, so volume expansions. So also here with the strain you can do negative epsilons. Sometimes that is physically realizable. For other cases where you would need to elongate a crystal, elongation can always be done. You can compress a crystal in one direction and pull it apart in the same direction. There it is always possible. For some other epsilons, you do not always get easily a negative value, but negative values are definitely possible. So I could have asked to do negative values as well, but somehow the task was not formulated that way. It would be more precise if you do negative values, because it's always easier to fit your parabola if you have the minimum included. So good observation. Certainly computationally negative epsilons are perfectly possible, and experimentally sometimes as well. If we do here the fit up to 0.03, then we find 35 GPa, and that would be the C4, that would be for the C44, and in materials project there is 32 here for the C44, so also that is in good agreement. The C12 can be determined from a deformation where epsilon xx and epsilon yy are equal to each other and non-zero. That you did as well. that gave this curve, where just one number was clearly off. And if we do here the fit, let's immediately look to the one up to 0.03, which is the most reliable one. Then the coefficient of the parabola is 143, and we had already, how much was it, 107 GPA for the C11. So if C11, which is 107, plus C12, which we search, is together 143, then the C12 should be 36 gigapascal. If you would do it with all epsilon values up to 0.12, it would be 2 gigapascal, so clearly not a very different number. And again, this one is the more reliable one. And this one too we can check with materials projects, and there somehow these numbers are different. You find 73 GPA here, which, when I made that exercise, I found surprising. I was not expecting this, especially not because everything else was in good agreement. So therefore, I repeated this exercise, which was here, so based on total energy, with the stress tensor methods, and I find very similar values for all elastic constants. So this confirms that this 36 is certainly the right order of magnitude. Quantum espresso behaves the same for the total energy method and the stress tensor methods, but in materials project this C12 is off. What could be the reason? Maybe there are higher precision settings used in these FASP calculations behind materials project, or maybe it's the pseudopotential that was particularly, that was not correct or not the best pseudopotential in one of the two cases. Or maybe this C12 is an unusually sensitive quantity. If you make small changes, that it has large effects on the C12. In order to test some of these hypotheses, I did high precision calculations where I now also indicate a plus or minus 10 GPA range, and here plus or minus 3 GPA range, to see could it, if my numbers would be a little bit different, could that give big changes in these C44? Can I have, for instance, a C44 that is 70 GPA, that is twice as large, by small modifications of my data points? And you see here the blue bands that are plus or minus 3 GPA. So, and these are already quite significant changes. So, no way that by small changes you will suddenly make this 70 GPA. My data clearly indicate it's in the neighborhood of 35 GPA. So that's that discrepancy is still not resolved. If somebody has a good idea why materials projects and this calculation here are so different for the sorry, I was discussing here C44, but the problematic one is C12. So if somebody has an idea why this discrepancy is there, I would still be interested to know that. Good. We are able now, at least in principle, to calculate these elastic constants. And the next thing we looked at were a few properties that depend on elastic constants. And that is something that several of you liked, because now suddenly, by knowing the elastic constants, you can calculate other properties up to the speed of sound in a crystal. And there were some examples given in the course here for FCC copper, where the speed of sound, an estimate for the melting temperature, another way to calculate the bulk modulus, the shear modulus, Young's modulus, Poisson's ratio, how they all are determined by the elastic constants. For this crystal, I asked you to verify the Born stability conditions, which are relations, constraints on the elastic constants that tell whether or not the crystal is stable. If the Born conditions are not met, then a deformation of a crystal could give rise to a runaway effect. You deform the crystal, you shear it, for instance, and then you release it, and rather than coming back, that is what a stable crystal would do, it would just keep shearing until it breaks. So such a crystal would not be stable against an elastic deformation. That would not be a stable crystal at all. And the Born stability conditions, they check that. So for this crystal, the 4 conditions, they are all satisfied, so no problem there. People wonder sometimes, is this the only criterion you can use for stability, or are there also other stability criteria? And yes, there are others, and we have met already some of these. For instance, the formation energy. That is a stability criterion. If the formation energy with respect to any other combination of elements that are part in that crystal, if that formation energy would be positive, then your crystal will disintegrate into these other crystals. This unit cell deformation, whether that one is coming back to the equilibrium or not, that is measured by the Born stability criteria. And there is a third set of stability criteria that have to do not with the deformation of the unit cell as a whole, but with the atomic motion inside the unit cell. And this is determined by phonons. So if you calculate the phonon spectrum and you find something which is called a soft mode, an imaginary phonon frequency, then your crystal will not be stable, not because deforming the unit cell would not bring it back, but because making the atoms move according to that particular phonon mode would rip the crystal apart. If you excite that phonon mode, for the atoms, they start moving, and rather than coming back and oscillate back and forth along an equilibrium, they would keep moving, and the crystal would disintegrate. So you have stability criteria at several levels. At the level of energy, at the level of the unit cell, and at the level of atomic motion within the unit cell. And with these elastic constants, you can then make all these other derived properties. Some of them exact properties, other estimates or proxies. Like the melting temperature, you can only very approximately predict from the elastic constants, whereas bulk and shear modulus, these are exact relations. We linked to a paper by de Jong and co-workers where you have the exact expressions for all these properties and their relation with the elastic constants. And also in materials project, these elastic constants, they are listed and they are calculated in the same way as in that paper by de Jong. As a matter of illustration, we also looked at a paper where a hard crystal was found, and a hardness is something um, that can be estimated from the elastic constants. And I hope that by looking at that paper that you realize what you can do already now with your DFT code, because that paper had somewhere in the caption minimal information about the crystal structure, but everything you need to know is there. With this you can make a unit cell of that crystal, and once you have the unit cell you can calculate the elastic constants and you can estimate the hardness, and you could do basically everything that was done in that paper. So this is knowledge that is already in your hands now. And I have repeated this here in a short scheme. You have, with this information and with the Bilbao server, you can make a P1 CIF file. You can put that in FindSim, and you have a fully symmetrized CIF file for that crystal. And on this one you then calculate the elastic constants. In many cases you don't have to calculate elastic constants because you can look them up in databases. And that's an interesting fact. Elastic constants is a nice example of a property that is nowadays so much easier to calculate than to measure. If you would look at all the crystals for which measurements of the full elastic tensor are available, well, that would be just a few hundreds of them, because this is experimentally quite involved. If you look in databases for computed elastic constants, on the other hand, you will find tens of thousands of crystals where this has been done. And with a precision that is, or with an accuracy rather, that is acceptable. So that may be a few percent off, but in many cases you expect this to be within a few percent of the true answer. So this is a piece of information, a physical property that is easier to get from a calculation than from a measurement. And the paper that did one of these first surveys, where several thousands of crystals were calculated with a systematic procedure to get the elastic constants, that was the one by de Jong that was mentioned a few slides ago. In order to illustrate this information from that paper that is also available in materials project, I asked you to look up the full elastic tensor of molybdenum carbide. And well, this was not this year, but some people asked or were confused and said, well, I look up the stress tensor of molybdenum carbide, but I don't find it. No, it's not the stress tensor that is documented. It's the elastic constant matrix. Remember where we started this module? You have stress, you have strain, and you have the elastic constants. The elastic constants translate strain into stress or the other way around. And it's the elastic constant that is a property of the material. Strain, that you determine how much strain you put on the crystal. Stress, that's the reaction that the crystal feels due to that strain. So these are not unique properties, but the elastic constants, that's a materials property. So that's the one that will be documented, not the stress tensor. And where do you find then that full elastic tensor of, say, molybdenum carbide? Well, I put here in the search window in Materials Project these two elements. I restrict the crystals to strictly two elements, and then I get this list of all crystals with only molybdenum and carbon. And molybdenum carbide, the ground state, the one that is on the convex hull, is this molybdenum 2 carbon. If you click on this and look in contributed data for mechanical properties, there you will find the elastic tensor that is called here the stiffness tensor. And the inverse of it is then the compliance tensor. And next to this you have all these elastic moduli in Voigt, in Royce, and in Voigt-Royce-Hill approximations. A question that was asked a few years ago and that I keep because it is a relevant one. Somebody wondered, how accurate are these elastic moduli? Because you calculate them on perfect crystals, while you measure them on polycrystals that even have a lot of defects and impurities. Now, the fact that you measure them on polycrystals, that is taken into account. That is what this Voigt-Royce-Hill scheme is meant for. And here you see very little, well, no difference between the different schemes, but for some crystals that will be much larger, and it's always the Voigt-Royce-Hill value that is expected to be most representative for a polycrystal. So polycrystallinity is taken into account in that way. The fact that there are defects in the crystal, that is not taken into account, but you could do that if you want by adding some impurities, calculate the elastic constants again, probably on a larger unit cell, or introduce even a dislocation or a vacancy or a cavity or a precipitate. If you have enough computational time, you could do that, and you could examine case by case what is the impact of these defects on the elastic constants. I can already tell you, in many cases, you don't see too much impact. It's the basic matrix, the basic host crystal that determines most of the elastic constants, and that is why values that have been calculated for single crystals, for pure crystals without defects, they are often good enough. They are reasonably in agreement with experiments, and they are so much easier to get than the similar experimental value that this is the thing that people will use. Good. With this, we completed our discussion on elastic constants. Let's have a quick look on next week. So we had now an engineering property, elasticity. The week before we had a chemistry property, chemical bond. The week therefore we had a physics property, electronic structure. Now we will look at how can we increase the types of systems that we can study. So 3D crystals was what we had so far, but can we also study impurities or defects, or even radically different things as surfaces? And so the answer to that is yes, and the way how will be discussed next week. And also next week we will discuss how reliable our DFT calculations are in terms of precision. How much do they depend on the computer code you use? And second aspect, accuracy. How close can you expect them to be to the experimental values? So that's the topic for next week. As this, one last look at the agenda that I shouldn't forget. So we are nearing the end of the term, the end of the course. So let's look at what will be the last few steps. So next week there will again be a feedback webinar. That will be the last one on course content. The week thereafter, for the people working on the project, the video and the paper are due. The Monday thereafter, we will have a feedback webinar about the project, where I will have a first brief look at what all of you did in the project. And again, 1 week later is the due date for the peer feedback of all of you on the projects of others. You will get specific information how to do that when we are at that point, when the projects have been submitted. Okay, so as this is pre-recorded, no possibility for questions, but I have answered the questions that I found in the reports. As usual, we have the summary and the exam question, but well, it's no use to let this play for 5 minutes as you are not listening live anyway. So also when you see this not live, please submit your contributions here. I will just scroll to the end. And yep, I survived this night recording, and I will see you back next week. Bye bye.